Today we're going to talk about analysis of covariance. Now, we're going to use a data set. It's an ortho-K data set, and it was an observational study. And so subjects were not randomized, but even if they were, this design would be appropriate. So one of the things we want to do is be able to control for differences between subjects so that and by control, I mean remove the variance for differences between subjects so that we have a more sensitive test of the treatment effects. In this particular data set, we have 3 lens types. And well, actually we have 2 lens types, but 3 groups because we've split one of the groups into 2 types of patients based on eye shape. The first 2 groups use a 5-curve spherical ortho-K lens, and the other group uses an aspherical 6-curve lens. Then we're going to look at their values. Our ultimate goal is their difference after 5 years of follow-up in terms of axial length. And in order to control for the differences between subjects, we're going to look to see where everybody started with their baseline axial length at the first measurement at their first visit before they started the lenses. So let's try this out. We'll go to Analyze, Analyze General Linear Model, Univariate, and we have as the dependent variable the axial length at 5 years. The fixed factor is lens type, and the covariate, which is a continuous variable, we stick down here under covariates. There's nothing to really do with the model. It's a full factorial model, and we're just going to, and really it's not factorial because there's 2 main effects, lens type 2 and baseline axial length. Factorial model means we would look at the interaction between these 2. We're not going to do that in this case. So then we look at options, and we can take the means. We're going to want to know the means for that lens type, because this analysis of covariance tests the null hypothesis that lens type 1 equals lens type 2 equals lens type 3. So a small p-value rejects that null hypothesis. But if it does, we're going to want to look and compare the pairs of lens types, and we're going to do that with the least significant difference test. So let's see what we get. Before I do that, I also want to show the parameter estimates in the statistics. Okay. So this is what we get. These are the between subjects factors, the 3 curves, the one eye type for the 5 curve, the other eye type, and the 6 curve. This is the number of subjects under each. Actually, it's the number of eyes under each. And here we get our source table, our sums of squares, familiar sums of squares. This is the sums of squares due to baseline. Now, the whole reason we're doing this is because when we come to our mean square error, we get Today we're going to talk about analysis of covariance. Before we do that though, we're going to talk about this study with 3 lenses. This is our ortho-K study, and it's actually 2 lenses with 1 lens having 2 types of eyes, and a 3rd lens, an aspheric lens, that we don't discriminate between the eyes. And then we're going to look at axial length over time, a 5-year follow-up. And so what would happen if we just went in and tested axial length at 5 years? We've done this before. We can go into compare means one way. Compare means one way Ancova. And we can look at axial length at 5 years and lens type. We can come down here with options, show our means, do the LSD test, and what do we get? We get a significant effect, and these are our means. If we look down at the differences, and we look at the 6 curve, it's significantly different. Everything is significantly different from everything else. The 2 5 curve means are different from each other. 5 and 6 are different. We've rejected the null hypothesis overall, as we see here. We've gone on to our post hoc and we've rejected everybody. Here we have our typical between within groups sums of squares. We take our sums of squares 51. There's 2 degrees of freedom because there are 3 groups. We divide the between subject sums of squares by the mean squares. We divide the within group sums of squares by the degrees of freedom for that, and we get a mean square of 1.015. Remember this number. Divide the 25 divided by 1, we get an F-test of 25, which is significant. Now, when we do that, this study design was not random. And people started out differently at baseline. And even if it had been a randomized controlled trial, people would still, some patients would still have different eye lengths when they started out. Maybe we'd like to get rid of this early initial, like to adjust for this initial axial length so that we can essentially statistically start everybody off with the same axial length. Then we adjust our means and we compare axial length at 5 years. And it's a much more direct comparison, and it gets rid of the between subjects variance. So that's what analysis of covariance does. So the covariate is axial length at baseline. And now we're going to test axial length at 5 years between these groups. So let's do this. Go down to our general linear model, univariate. We're going to pick our dependent variable as axial length at 5 years. Our independent variable is the 3 lens types. And our covariate, which we put down here, all continuous variables come down here. So axial length at baseline is a continuous variable as opposed to a categorical variable, which is a fixed factor that goes up here. We're going to look at our options, which is we're going to select our lens type 2. We're going to compare our main effects and do the LSD, just as we did in the one way. And we're going to check this box to look at our parameter estimates, because this will show us that we get coefficients for all these just as if we had done a regression equation. All right, so let's see what we get. Here we have our sample size. Notice we've rejected the null hypothesis of, first of all, the baseline variable. We have found that, for example, down here, and this is our parameter estimates, this is the slope of baseline. So for every unit change in axial length at baseline, there was almost a 1-point change in axial length at follow-up. We have our 2 groups, which the 2 lens types are compared. Here we see the sums of squares for the axial length 0 is 329. Now, what's really cool about the analysis of covariance is this sum of squared is subtracted from the total when you're comparing the lens type 2 and its error. So now when we divide our remaining sums of squares after we've accounted for this. Before, this 329 sums of squares was included in this 55. So now we've taken it out. And instead of an error term that was 1, had a 1 in it, 1.015, now our error term is 0.146. This is the denominator for the f-test. So our lens type f-test now is 506. Before, it was 25 for lens type. Now, it doesn't say lens type over here, but that's what the between groups is. It's the lens type. And so that's quite a boost for our f-test. And if we come down here, we see actually kind of a different result. Remember before up here in our multiple comparisons, everything was different from everything else. And now, even though our test is more sensitive, it doesn't show a difference between the 6 curve and the 5 curve, which is the oblate eye. It's the spherical lens with an oblate eye, not different from the aspheric curve. However, the 5 curve, 2 5 curves are significantly different, and the 6 and the round eye are very different. And our means are over here. If we look at the graphs of these two, this was the graph from the first analysis, just the straight one-way analysis. And we get a shape that looks like this. And here we have the study with analysis of covariance. So what happened was that the baselines weren't equivalent between the groups. So you can see, for example, we have a lot of, well, the open circles here are the 6 curves, and the little black dots are the curves, are the points. This is follow-up axial length on baseline. The little black dots represent the oblate eyes, and the triangles are the round spherical eyes with the 5 curve. You can see why this graph is correct, because after you've adjusted for baseline, the black dots just completely overlap around the open circles. Those 2 points, there's an example of a null hypothesis that looks pretty true. And this is an example of a null hypothesis when compared to these other 2 that's clearly rejected. We didn't get that when we just did the Ancova. The analysis of covariance is a much more accurate picture of what's going on. So analysis of covariance is a very powerful assumption, or a very powerful analysis.